So welcome back, everyone. So we're going to start a new lecture, a new section today on dimensionality reduction. So I'm sorry if I'm a little bit disorganized or kind of. So today there was a giant tree that fell down in the smaller windstorm this afternoon. It made through the 1 September, but not apparently the one so last night. And there's a crew of construction here with a crane that might be sawing. You might hear some chainsaws in the background. So before we get into the lecture, just quickly, where are we in the schedule? So we finished kind of, we talked about this background section, and we did a bunch of stuff on linear algebra. And then we applied this in two areas so far. One is in linear regression, which is I think mostly, other than how you solve it, a fairly straightforward, very simple application of linear algebra. In gradient descent, we showed how to optimize these kind of high dimensional functions, and linear algebra allows us to speak about vectors, so to generalize to high dimensions. What we mainly talked about 2D, where you could visualize it, but it extends naturally to higher dimensions where you can't very easily draw a picture. So today we're going to start a new section on dimensionality reduction, which is going to use linear algebra like much more intensely, right? It's going to use a lot of this core idea of the kind of orthogonality and this notion of spans and subspaces, and this is really going to be key. So we're going to start today. The lecture today is going to be about this operation called the singular value decomposition, the SVD. And then we will talk about its relation to rank K approximation, eigenvectors, and how this kind of, and today also we'll talk about this formulation of a low dimensional subspace approximation. Okay, so the idea is you have data in very high dimensions. We want to represent it in low dimensions. That's the basic idea of dimensional reduction, if you couldn't guess from the name, but we'll try and put this into some context. Okay. Also on the schedule, quiz 4 is today. This will be on gradient descent. It will be open at 2:30. So I will end the lecture by 2:30, so you can start that quiz. It's going to be on gradient descent. Again, you're going to get this one sheet of paper, one side, that you're going to turn in. Hopefully you've created this note sheet. You have until 11:59 to finish it. Again, you get half an hour. We'll again hope it takes on average about 15 minutes. So that'll be just on those previous three lectures, not on the material we discussed today in class. And then the homework 3 is going to be due on Wednesday. So so if you have questions about that, myself and the TAs have been getting some questions. One thing to point out, let's see, in the bonus, I said do any better than the rest of the class for part B. I meant part D. You can use any technique that you want. So if you put extra effort into this and you do better, we'll give you a few extra points. These points can go above 100%. So even if you get 100%, you can get 105% perhaps. So the function 2, if you haven't looked at it, the key will really be looking at that collab thing I showed you in class the other day and moving around the range you plot in and the levels that you plot. And that's going to be kind of a key insight you're going to want to use to figure out what function F2 looks like. It's going to have a single minimum. I'll tell you that. This is kind of common of these modern problems in data analysis, but it's not necessarily going to be convex. But gradient descent will still converge. The question is how fast and what technique to use. How do you choose the choice of the kind of the learning rate and so forth. Oh, okay. So I'm seeing that it's not readable and the videos is low quality. Let me see if I can do something really quick. Hopefully the tree didn't cut our fiber. But let me just check something quick. Okay, I'm getting, if that's happening, it's probably on your end. It looks like my internet, my upload speed is like 400 megabytes. So I, or above, so I think I should be okay. Yes, okay. Oh, okay, let me, maybe this is the issue. Maybe I'll try this. Let's see. Okay, good. So I wonder if the issue was, oh, okay. So this fixes it for you. Ah, okay. I will do this in the future. What happened is it's recreating my iPad screen on my computer, but I made it small so I could see it while everything else. But I guess that then it only displayed at that resolution. Okay, great. So this should fix the issue. That B down here should be a D. Okay, great, good. So thanks for pointing that out. Okay. So let's so let's get on with the lecture. Okay. So dimensional reduction. So this is okay. So we're going to be talking about this problem, and we're going to have the idea of we have input data, and we'll be saying that this is A in an element of R N cross D. Okay, so this is a N cross D matrix, but we'll think of it as a matrix, but I like to think of it as a subset RD. So that think of it as A as actually being A1, A2, and these are the rows of A. So each row AI is in RD. Yeah. So it should be recording. I can see it live on YouTube. Okay. So this is so I like to think of this as instead of just a matrix of data, these are going to be points in some very high dimensional space. The premise is that this D, right, this same D here, this is the dimensionality D, and we're going to say that it's really high dimensional space, and we don't actually need that high of a dimension to do the data analysis is what we think. We like to bring it down to a lower dimensional space, maybe down to 2 dimensions or 3 dimensions where we can visualize what's going on. Okay, or we will have an algorithm that's going to run on this data, and one of the potential issues is that the runtime of the algorithm will depend on the dimensionality. Maybe it just takes that long to read each data point and we need to make a bunch of loops through it or something like that. So we'd rather first compress the data before we run the actual algorithm. Or there's, so the reasons for doing this are, say too high for viz. So the runtime could depend on D, or in some cases, there's some statistical kind of formulation where there's the signal versus the noise, and we think that there's basically only k dimensions which determine the signal, and there's d minus k dimensions, which are basically just noise from the model. Okay, we don't think really there are that many dimensions saying what's going on, but we record coordinates and there's noise every time we're recording something, and so we think outside of those other k dimensions, there's probably some, that's probably noise. So if we can reduce the dimensionality, we're going to get rid of that noise, and the analysis afterwards going to be more robust, hopefully. Just focusing on just focusing on the signal part of it. Okay, so there are a bunch of ways of how to do this. There are these nonlinear dimensional height reduction techniques. There's there's these random projection techniques. We're not going to talk about those in this course. We're going to take basically the route of things based on related to principal component analysis, which is this linear approach. We're going to start with data as a matrix A in R, N, D. Then we're going to use an operation called a singular value decomposition. Okay, this is going to be similar to an eigenvalue decomposition, and I think in the next lecture I'll explain this connection more deeply. And so this is going to map us, is going to map A, or each AI, there's some mapping function. Let me just not use from F that maps to, let's call this BI. And BI will, well, is it going to be in RD or is it going to be in RK? But it's going to be in a k-dimensional subspace. Okay, it still might, there are different ways to interpret this. It could still live in the full dimensional space, but restricted to a subspace, or we can actually operate only on this low dimensional subspace, this k-dimensional subspace. Okay, and so I'll try and draw some pictures going from like 3 to 2 dimensions, but this is useful when going from like 10,000 dimensions down to, in this case, could be 2 or 3 dimensions, could be 10, could be 100, but we're really reducing. So kind of the way to think about this in your head is that D might be something like 10,000, and we're going to go to K, which could be 2, could be 3, it could be 10, maybe it's going to be 100. Okay, you know, it's not clear what K needs to be. We'll often try and get it down as low as we reasonably can, and we'll discuss this you know, how do you answer what the right value of K is supposed to be here. So okay, okay, so let's see. Before I get into it, I want to also say that this is going to be unsupervised, so learning. Okay, so I said that regression was supervised learning, and that was so the input is going to be A, right? Not say X, Y. Okay, so there are no labels. Okay, so that I don't get these labels Y that tell me I'm trying to predict some value Y. I don't have access to that. Okay, so this is going to make it so I'm not going to be easily going to be able to very generally measure error through things like generalization and cross-validation. I'm basically just relying on the data itself. I'm saying I'm trying to find a simpler representation of data, right? So the goal is just a simpler representation of the data. It's not to necessarily make a prediction. Sometimes this is useful within a prediction, right? You do dimensional reduction first, and then you run regression, right? This is something called principal component, so principal component regression. Or you do it, then you do clustering or classification, and this can be part of the pipeline. You can use it to then do visualization to inspect your data or to speed up algorithms. But it's not actually, I don't have a clean kind of prediction of, or a single score I can say how well this is really doing. We'll write down a score, but it's not something that there's going to necessarily be a sweet spot of what the right value K is. And this makes it tricky. We also can't rely on just measuring in this Y direction to determine, to optimize over. Okay, so we're optimizing over the data itself. Okay, so we're optimizing over A to B, right? There's this B subspace that we're finding, but it's really has to do with kind of the structure within A, not respect to this other label that we have going on here. Okay, so this means that our A is going to be what I call a data matrix. And I mean something specific by this in the book. And I like to make a distinction about this. Some people might use this use this terminology to mean more general things, but I'm pretty specific about this. I think this is important. I think a lot of mistakes are made by not specifying this. Okay, there is a question. Isn't your goal still based on prediction? You want a prediction for a new low-dimensional data to be the same as high-dimensional data. Well, okay, so you might do a prediction afterwards, but you might not. You might just visualize it and then trying to use your eyes to make some inference of what's going on, to spot outliers, or to you have some algorithm you're trying to do, which might not be a prediction algorithm. It might be you're trying to speed up some sort of scientific simulation. This is used within that context as well. There are certain other things where the SVD, which is the core thing we're going to talk about today, which is kind of the core for PCA, is used inside of predictions explicitly, or is trying to, we'll talk about something in the last lecture in this section called multidimensional scaling, where your goal is you're given just a bunch of distances, not data, but distances, like the airline cost between two cities, and you're trying to put that in a two-dimensional subspace so you can kind of get a picture of it. That's not really prediction, but you're trying to get a two-dimensional subspace representation of it to kind of understand what's going on. But you're not necessarily making predictions here. And the same thing is going to hold in clustering as well. Clustering is not also a tool for a prediction. This is unsupervised learning. It's, I have kids, and what I've figured out about unsupervised learning is that if I'm not watching over them when they're doing online school, they're probably having a bit more fun than they should be, but they sometimes get into trouble because there's not someone watching over their shoulder to guide them about what's going on here. Okay, so it's kind of, there's not this label that's guiding you in what you should be doing. Okay, but how can you tell your data reduction is a good representation until you test it? Okay, great. So what we're going to come up with a formulation that's going, and I'll get to this in a couple slides. I'm building up to it, but I need to kind of specify some ground rules first. Is that we're going to say, the distances and what the original data is saying is good, that we understand how to measure distances and variance and things like that. And we're going to try and find a low dimensional representation that captures as much of that as possible while being in a low dimension. And we believe if we're doing that well, then hopefully this other stuff carries over. There are some, you can kind of back engineer some statistical models where you say, well, let's assume that data came from a low dimensional subspace with noise under Gaussian noise, and then we're going to say, well, let's uncover the most likely Gaussian subspace that data could have come from if it had some sort of Gaussian noise. So you can come up with a formulation like that. I think that's kind of a post hoc formulation of what's going on, but it could be useful nonetheless. We're not going to explicitly do that, but hopefully we'll see sum of squares error come up again, and you can kind of imagine that there's a way to get there from a statistical kind of starting point as well. Yeah, so this is trickier, and this leads people to use this for things it's not intended to be used for, right? This class, the way I'm teaching this class, and I hope the way you learn data science at Utah, is not just, here are some tools, let's apply them on data and make some grand conclusions, but let's understand what they're actually doing, when you can use them and when you really shouldn't be using them because it doesn't make sense, right? I'll tell you, this comes up all over the place as a core within a bunch of subroutines that you'll see as you go on and do even cooler stuff. But the initial, any unsupervised problem is kind of, you're trying to find structure in the data and simplify it. You're not trying to make a prediction. Okay. So hopefully these are great questions. I'm glad to spend time on them. Hopefully this will make more sense as we get through the formulation. Okay, so ground rules, right? Ground rules. We should not always do this. There are techniques later on in the book, if you read beyond what we cover in this course, that talks about issues and sometimes going beyond this. But a data matrix, I mean something specific by this, right? So again, this is A in R, N, D. And let me give some examples before I say what it is I mean by this, just to kind of make sure it's clear what are positive examples before I give you some negative ones. Okay, so there's a kind of a cool data set by a collaborator of mine at the university where they have N of these of these weather stations. Okay, and they measure temperature, and they measure the like temperature at time points. Okay, so they have like 40,000 weather stations they keep track of around the US, and they have and they've been doing this for years, but let's say if it's once every day, then that's 365 of these time points in a year. They measure the temperature at noon or something like that. If they collect them usually every hour or maybe more frequent than that, and then it's 365 times 24, of these weather stations, right? So I'm always going to think of having a matrix A, right? And this is N, and this is D. N could be the number of weather stations, and each weather station gives me a reading, right? AI. This is now one weather station. Okay, and it's got D time points it's read. Okay, each thing is temperature in Fahrenheit, something like that. Okay, and I think there's some pattern going on here among the weather stations I want to figure out, a simple pattern. Okay, another example might be, so I've got N, so movies, N, let's see how it matches my notes. I have N users who rate D, movies, right? So Netflix or Amazon or IMDb famously have a lot of users who are watching these movies, and they have a lot of movies, but they probably have kind of I don't know, they may have way more users, people watching them than there are actually these movies. And you might think that there's some kind of correlation between them. If you like like one Indiana Jones movie, you're more likely to enjoy the new one that's coming out next year, kind of, if everything goes well, apparently. So there's something, if you like action movies, you probably tend to like other action movies. If you like rom-coms, you tend to like that. And there's some kind of lower dimensional, think subspace, that's governing which movies you actually like based on these ratings. So they have, Netflix, they have this way of understanding whether you like a movie or not based on how much you actually watch of it, and whether you put in your list. And they used to have a way where you could actually rate them. They got rid of that because they found it not helpful. But they internally store some effective score for each user of how much they liked a movie that they watched, right? And so they use this to kind of understand a subspace of these movies. And there is there ends up being this lower dimensional, maybe it's 20-dimensional subspace that describes people's kind of how well they like movies. That might not capture all the variation among people, but might be very useful in filling in data when you don't know someone's going to like a movie or not. Okay, there's another example. So let's say I'm going to have stock, so prices. Okay, I'm going to do this something a little bit different now. I'm going to keep track of this. Let's say the closing price for n, days, right? So 1, 2, up to d, d plus 1, up to n minus 1, up to n, right? So I've got the stock price for these n days in this array. And what I'm going to do is I'm going to what's called shingle this. I'm going to group them into sets of say 25 days. Let's say d equals 25. And I want to use, and what they'll do is they'll use this in a prediction of what the closing stock price is going to be on the next day. Okay. And then I'm going to do this. I'm going to make a data set where I'm going to do this again. I'm going to slide the window over by 1 and get this other 25-dimensional data set. All right. Okay. So I'm going to go from n to lowercase n is going to be n minus d, and d is going to be, let's say, 25 days. Okay, and now I can use the next one as a y and make some sort of prediction. But there's often a lower dimensional kind of structure going on here. So this is called like an autoregressive time series model, where you can make a regression prediction this way. But what they often find is that you want to take something like 25 days or 14 days, something like that, to make the prediction. But that this is kind of noisy, so you want to find a low-dimensional subspace. So you'll create this matrix, which is going to be n by d, and then you'll want to compress it using, kind of principal component analysis or something like that, to n by k to get rid of a bunch of the noise that's going on, and then you might make a prediction from this representation. Okay, so this is, n to the minus d plus 1. Thank you, Hassan. Okay. Or plus 1, where's the, there, okay. So I might have it off by 1 error here. It depends on whether you need the next value to use in the prediction, how I keep track of that. Okay, but this is another way of getting one of these sort of data matrices. Okay, so, and the other thing that's going on, you could think of taking an image of something, like an object, like they did this, there's something that's called like the Utah teapot. It's a little teapot, which is one of the first things they ever did this with, where they took the image and it's a fixed camera and a fixed thing, but then they rotated the teapot. They just rotated along one axis and they kept taking pictures of it or depth kind of senses of it. And so there's one dimension is changing. It's just rotating. One dimension is capturing that, but they're getting back a bunch of these pixels with these values. Each value is like a dimension, and they get lots and lots of these pictures. There should be a one-dimensional representation of what that rotation is doing. Can we recover that from this data? Right? That might not be a linear thing, but it's clearly one-dimensional. That's all that's changing is the one, or maybe we rotate it and we change the lighting condition by turning the lights up and down. Now that's two-dimensional, right? There's clearly some two-dimensional subspace going on here. Can we recover that? And the rest of it should be noise somehow. Okay, so these are a lot of places that's coming up. What I want to highlight, which is really important here, is that all coordinates have the same, so units. Okay, all the coordinates have the same units here, because what I'm going to be doing is I'm going to taking one data point AI, I'm taking another data point AJ, and I'm going to be using deep within inside the analysis the Euclidean distance between them. This is the Euclidean distance. That means what's going on under the hood here is that I'm taking these two data points in RD. I'm doing AI index, let's make this L, index L, minus AI AJL, right, squared, and I'm taking the square root of this, right? This is the definition of the Euclidean distance. And, okay, so if they're the same coordinate, if this is measuring the Lth coordinate versus the Lth coordinate. So this is Lth coordinate, and that's okay. Those should be really measuring the same thing with any sort of data matrix. But this is adding adding something about the coordinates, and I haven't somehow removed the units. So if the first coordinate is measuring apples and the second coordinate is measuring oranges, I'm literally comparing apples and oranges, which you aren't supposed to do, right? Well, maybe you can compare them and say one's green and one's orange or something like that, but you know, and from a data analysis perspective, you shouldn't be doing that. If remember the example where I had this web page and I had the scroll time and the amount of time on the web page and the wiggle the jiggle of the mouse, I shouldn't compare those. Those were different units, right? If I have height and weight of people, I shouldn't compare them in this way. This does not make any sense. Okay, so I want to be doing this on applications where all the coordinates effectively are doing the same thing. They're all measuring temperature. They're all measuring a stock price, right? They're all measuring the rating of a movie from one user. That kind of needs to underlie this, or the next things I'm doing are not going to make sense. There are some very famous kind of textbooks and examples where they'll run PCA on data sets where this is not true, and you look at it and you're like, that doesn't make any sense what they're doing. And there's some like things you can do, like normalizing the coordinates or something that is supposed to remove the units, but that's destroying a bunch of your information. It's not clear what the effect of that. It's outliers can throw that off. If you have one data point in, you get a completely different answer than if you don't have that data point in, right? That's not a very good operation to be doing. So we need to have this property that all the coordinates have the same units, right? And really mean the same thing. This is like super important. Otherwise, this isn't going to make sense. Okay, and the whole formulation, we're eventually going to get to kind of a cost function, which we're going to try and optimize. And that's only going to make sense if we're allowed to take Euclidean distance between two of the data points, two of the rows, or the L2 norm, or any of the norms. It doesn't matter which norm we do. They're all adding up components from each of the coordinates. Okay. Okay. Good. So Okay, so I want to get now to the cost function, but I need to talk a little bit about idea of projections. Okay, there's kind of a linear algebraic way, or a numerical linear algebraic way to approach this problem. There's probably a statistical one. I'm going to give you a geometric view of how to get here, and we're going to understand kind of principal component analysis and SVD through geometric point of view, and that's projecting from a high dimensional space to a low dimensional space. Remember, our goal is from A to B, and B is basically, we can think of it as, well, it's going to be a subset of RD, but effectively think of it as a matrix, and the rank of B is going to be equal to K. Okay, so we're going to think of a picture where we have data in this high dimensional space. All right, so this is something like RD, and we have these data points, A1, A2. Okay, and we're going to try and find this subspace in here. Right, there's some subspace here. This is going to be B essentially. Okay, or the subspace spanned by B. Maybe this will be the span of B. And we're going to basically be projecting each point onto this low dimensional subspace here. Okay, this is going to kind of be the right thing here, and these are going to be orthogonal projections. So what we're going to get is this, if this is, let's see, where can I have room to draw? If this is A3, then this is going to be pi of B, projection onto B of A3. That's going to be this point right there. Okay, so let's write this down. We're going to be projecting these AI from RD to the span of this subspace B, which we're going to be finding. That's how we're going to reduce the dimension by being on this low dimensional space, right? And we're going to denote this by pi of B of AI. Okay, and it's going to be a little bit ambiguous what dimension this is in, because there are two ways to think about it, either RD or lower dimensional k-dimensional subspace. So we're gonna go through those and see those two views of what's going on. Okay, and I'm going to start with a simpler case. Let B be one dimensional V, right? So now V, let's draw this on here. So V is going to be this vector, and notably V will go through the origin for now. Okay, so V will include the origin on here. So I'm going to have one-dimensional vector V, which is going to be a vector in RD, d-dimensional vector. And let's say that, for simplicity, that V is going to be a unit vector. Okay, so its norm is going to be 1. This is typically what we're going to want and what we're going to find. So then I can write the projection onto V of AI. Okay, and this we actually should know how to do already. This is going to come out from the dot product. So I'm going to project AI onto V. This gives me the length of our projection. This gives me the length of here. Once I have A3, I project it onto this light blue vector, and it gives me this, the dot product tells me the length on that subspace restricted to the one dimensions. But we might want to actually recover this. So we're going to say that this is multiplying by this vector V. That will give us the actual data point here, projecting onto this, right? So again, the picture is V. This is the origin. We're going to have a data point A, and we're going to project onto here. This is pi of V of A. Okay, and we can just recover this with the dot product V A dot V times V, right? That's what this projection is going to be. Okay, and so this is kind of the basic geometric operation that you get out of the dot product here. Okay, okay. So how are we going to solve this in general? So in general, now for k-dimensional subspace B, okay, we're going to represent this not just by one vector v, but by k of these vector v's. Okay, so we're going to describe this set of these, this, we'll call this orthogonal basis, VB, which is going to be the set V1, V2, up to Vk. Okay, and we're going to restrict that each Vi is going to be a unit vector. Okay, each pair Vi and Vj will have, for I not equal to j, it's going to be Vi, Vj, it's going to be 0. This means that these are going to be orthogonal to each other. Okay, they're going to be a right angle between them, which we established by the dot product being 0. Okay, and for any x and b, then it means we can recover x is going to be this sum alpha j vj, where alpha j is a scalar, which is just going to be x vj, right? So this is going to be the same, the scalar value here is just this dot product. Okay, so I'm going to be able to recover, we're going to be able to recover any point exactly on B. We're going to be able to represent it in this orthogonal basis. Okay, so we're using the V vectors to create a space to map all the points onto. Yeah, right, so I'm getting up to how do we define a projection onto B, and that's the space we're going to project onto. And then we're going to say, well, how do we find the best B? And by best B, that'll be by the best representation by V orthogonal basis vectors, by K orthogonal basis vectors, which is the set V. Yeah, great. Good, so that if that question indicates that I'm leading you on the right path, great. Okay, so now, so I'm gonna want to write the projection onto B for a data point A is then, it means that I can write this as j equals 1 up to k of Vj A Vj, right? So every time I'm getting, so in this case, each of these, I'll use a different color here. Each of these entities here is a vector in RD, but it's restricted to be along one of these basis vectors, right? And I have k of them, I'm adding them up. Okay, I'm adding up these k, the components of these k basis vectors, and they are going to recover this projection, right? So if A was already a point in the subspace B, then I'm going to get back that point exactly. But if it's off the subspace, then it's going, I'm not going to get it back exactly. I can't represent it, right? So if I have if I have this subspace, right, and I can think of this as being this subspace here, and I have a point, and it could be negative also, right? But if I have a point A and its closest point is here, right? What's going on? I can think of this one as being V1, this one as being V2. So I'm going to get two components here. I'm going to get a component here. This is the projection onto V1 of A. This is the, right here, this is the projection onto V2 of A. And this is the projection onto B of A. Okay, so it's the sum of those two vectors. I'm living in this high dimensional space, and I can add two vectors together. I get all their coordinates. Okay, add together all their coordinates. Okay, so yeah, this is what the projection is doing. And what's really useful here is to, think about these two values. This is alpha 1. I already used red. Okay, let me use a different color here. Okay, there's two values here. This is alpha 1. Remember, this is A V1, and this is alpha 2, and this is A dot V2 is alpha 2. Those are lengths. Okay, so what does this kind of look like here? It looks actually like a coordinate system, right? If V1 happened to be just the x-axis, the vector 1, 0, 0, 0, 0, 0, and V2 was the y-axis, the vector 0, 1, 0, 0, 0, 0, then all I'm getting back is the first two coordinates of the data point A. And then it has to live in this xy plane, and I'm getting back those first two coordinates of that data point. But it can also be rotated up off the plane. The subspace might be rotated, and these subspaces, V1 and V2, might have a jumbled whole bunch of the different coordinates, right? It's not just one of those coordinates. But it's useful to keep in mind it could be the original coordinate system. But what this is doing is it's effectively giving me a new k-dimensional coordinate system. So I can also represent this. Also, I can think of this vector as this A1, alpha 1, alpha 2, right? As this two, or in general, alpha k. Write this. Which is going to be a point in Rk, right? I can use this new coordinate system, right, to give me a k-dimensional representation too. I've decomposed into these orthogonal components, and I just take the amount of direction along each of those orthogonal components. There are only k of them. That gives me a k-dimensional representation. Okay. If I look at this full green vector, I've highlighted it in green here, right? This whole thing, this lives in d-dimensional space. That's a d-dimensional vector. But there are only k of them, and so the span of those k d-dimensional vectors is only k, and there's a different k-dimensional coordinate system here also. There's also this k-dimensional representation. Okay, so there's a little bit of confusion when I say this dimensional reduction by projection. Am I getting a d-dimensional point or a k-dimensional point? Well, it depends on what you want, right? If I want to compare how far away it is, right? If I want to compare, kind of measure this distance, right? How far did I project? Well, then I need the d-dimensional point. But if I want to use it in visualization for 2 dimensions, well, then I want those 2-dimensional coordinates, right? So both of these representations have some uses, and we'll take advantage of both of those. But it's a little confusing that it could be d or it could be k dimensions depending on what output representation you take. Okay, great. Okay, so finally, let's talk about. We have 15 minutes left. We'll define the problem, and maybe I'll mention the SVD, and then we'll spend more time on this in the next lecture. We'll stop for the quiz. Sum of squared errors. Okay, so now we want to come up with our sum of squared errors formulation. Okay, and we're going to say this as sum of squared errors between A and B is going to be, again, it's going to be a sum of these data points, AI minus the projection onto the subspace defined by B squared, right? So remember these this light blue distance over here that I highlighted, that's one distance, and we're gonna add, square those and add those up, right? And then the goal is the best, so k-dimensional subspace B, and this will be represented by VB, right, which are these k orthogonal vectors, to minimize equals arg min B sum of squared errors of A, B, right? So we want to find the one that if I look at all the cost of projecting a data point onto that subspace, I square each of those and I add those up, that's as small as possible. Okay, and so this distance, this light blue distance, right? This distance here, again, this is measuring an L2 distance. This is Euclidean distance between these data points. So it better make sense to define a distance. It better make sense to add up those coordinates in some way. So they better all mean the same thing. Otherwise, this formulation is pretty nonsensical. People use it even when this isn't true, but in this class, I only want you to be using it and thinking about it when this is the case. Okay. Right, so yeah. Okay, so this is our goal for this. We're going to say two things. So SVD is going to solve for B such that B contains the origin, right, which is 0, 0, 0, right? So it contains the all zero vector. PCA has no origin restriction. Okay, so we're going to be talking about this first problem for the next this lecture and the next two afterwards, the SVD version of the problem. SVD is actually a decomposition, but it's going to give us the solution. PCA is a slight extension of this that does not require the origin to be included. And this distinction can be pretty important in some very low dimensional cases. So this is principal component analysis. Okay, so it's going to be a very simple trick. You're going to do something called centering, and that's going to handle it. But we're going to delay that for a while. Let's just talk about this SVD. This is kind of a simpler way to think about it. And the difference is akin to if we were restricting that our linear regression thing had an offset or didn't have an offset. It's going to be a similarly simple trick. It's different, a little bit different what we do, but it's basically that simple. Okay, so we'll come back to that. Okay, good. So I have time to tell you about the singular value decomposition. Okay, we're going to try and yeah, today I'm gonna tell you how to use the SVD to get the answer, the optimal answer again. Again, this is the SVD. So we're talking about the singular value decomposition. Okay, often just written the SVD. I think this is like from the 1950s. It's kind of a linear algebraic notion. I think came up as early as the 1950s. They may not have originally realized it solved this problem, but it's kind of this older kind of thing from linear algebra. It is like one of the fundamental things in numerical linear algebra kind of packages. So it's available built into most languages. In fact, there's this old Fortran code called called LAPACK, right? This was written in Fortran. Fortran is kind of like C. It basically, you can compile it directly into C. This is highly optimized. This is a marvel of engineering, maybe one of the most important marvels of engineering that underlies a huge amount of data analysis that you might otherwise not be aware of. But every programming language basically calls the same package called LAPACK, which is designed by, and optimized over several years, 30 or 40 years ago. And it almost hasn't changed, right? They've been basically using the same thing. It's not quite true if you take the data mining class. We'll talk about like sketching, and there's the idea if you have really huge data, you might want to do something simpler if you don't need as much precision in the answer. But this is basically built in. You call it in Python, you call it in C, and Java, and R, and MATLAB. In anything, it's going to call the same backend library to compute the SVD. There are several ways to do it, and it kind of identifies what's going on. If it's done correctly, it identifies the characteristics of the problem and then calls the right algorithm under the hood. It's kind of like, think there are lots of ways to sort a list. And it kind of identifies, well, is it short? Is it long? Are the digits not too far? Are they partially ordered? And it figures that out and calls the right subroutine. We'll see one of them in a couple lectures, so you get some grounding, but there are other ways of how to do it as well. Okay, so the SVD, let's see, it's going to, the input is going to be a matrix in R, N times D. Hopefully you guys aren't hearing that chainsaw in the background. I warned you about that. Okay, and it's going to output, this down here, it's going to output 3 matrices. Okay, and the exact structure of these is pretty much the same thing, but Python does it a little bit different than most other languages, which is a little bit confusing. So U is going to be a n by n matrix. So typically D is less than, I'm going to give examples where D is less than n, right? So that means that U is going to be bigger than A. It's kind of wasting stuff. In fact, it's a bigger representation than the original data. N's going to be dense, so you're filling this all up. But we're going to see, you can ignore most of it. Okay, it's going to be S, which is going to be another matrix, which is n by D. And you're going to get V, which is going to be a matrix that's in D by D. Okay, so even if you can do the same thing if n was less than D, but then V is going to be this bigger matrix, because then that one's D by D. Okay, but it's going to have the property that that I can recover A by U times S times V transpose. Okay, right? These can multiply together if I represent them this way. And so it's going to give me back an n by D matrix. I have an n by n by an n by D by a D by D. All right, so I can multiply these together, and this will recover A. Okay, And it's going to have a very special structure. So these two are going to be orthogonal. So U and V are going to be these orthogonal matrices. So these are going to be orthogonal, which means that they're just kind of changing the basis. This is where we're going to get some basis representation. That's going to be the V. Is going to come out of the V matrix. And then the S matrix, right, this S matrix here is going to be kind of the scaling matrix. This is going to be a diagonal matrix. And so I can represent this as S equals to diag of, and we're going to call this sigma 1, sigma 2 up to sigma d. And so that means it's going to have structure sigma 1, sigma 2 up to sigma d. And this are all going to be zeros. And then down here is also going to be zeros. Okay, so it's going to be, it's not square, but it might have more rows than columns. And then those rest are just going to be all zeros down there also. Yeah. Yeah, the transpose is only on the V. Yeah, thanks. Okay. Okay, so the U and the V are basically allowing us to represent some basis structure, and we're going to pick off the ones that we want. And then the S is going to tell us how much to scale along these basis things. Okay, I'm going to write this, and I like to draw a picture like this. I like to think about these as rectangles, where this is N by D. And this is going to equal the product of three matrices. U is N by N. Okay, I'm going to get a, I'll do orange here. Okay, what do I have left over? Let's do pink. S is going to look like this. It's going to be the same dimensions as A, N by D. And then I'm going to get V transpose. V transpose, which is D by D. Well, it was V is D by D, so D transpose is also D by D. So S is going to be related to the eigenvalues. So I'm only going to have values on here on this diagonal. These are going to be what's called the singular values, and they're going to be related to the eigenvalues. This part kind of down here, this is always all zeros. Okay, so that means I'm going to be multiplying part of U. It's going to be multiplying by here, and I know that's going to be all zeros, so this is going to be all zeros also, right? So these guys, this is all zeros, so this is kind of don't care. It's going to be an orthogonal matrix, so all the rows, all the columns are going to be orthogonal from each other, right? So all of these, each UI is going to have equals to 1, and uj dot ui is going to be equal to 0. But otherwise, after the first D, I don't care at all, because I'm going to be multiplying them by zeros. They just need to fill out the orthogonal basis in this n-dimensional space. Okay. Okay. So what I'm going to ultimately do in the last minute I have left, and then we'll clearly review this more, is I'm going to call this the top K that I want. I'm going to change these to make these to be 0. Right? So this is going to get zeroed out. Then, so this will zero out. A bunch of this stuff will zero out, and this stuff will be zeroing out. I'm going to get left V1, V2, V3. These are ordered. So sigma 1 will be greater than sigma 2, greater than kind of greater or equal up to sigma d. And so that's zeroed out. And what's left are these V1, V2, V3. And so my best, subspace VB is going to be equal to exactly this V1, V2 up to VK. This singular values, these, what's left here, these guys, the ones which are remaining, those are going to tell me how much scaling, how much information is in there. And the top one, the sigma 1 is going to be the largest. Okay, and these are going to be a square root of the eigenvalues of the appropriate matrix. And so the ones that contain more information, well, those are associated. Basically, this guy right here, the top one, corresponds with this top one here. So sigma 1 corresponds with V1, sigma 2, V2. And so I'm going to take the top of these, and this tells me how much information I capture. If I take the top K of them, that's going to be the best subspace. Okay. Okay, so I've run out of time for this lecture. We will start here. We will review this picture and some of the structure, and then we'll walk through an example at the start of the next lecture. And we'll talk a little bit more about that and the deeper connection to the eigenvectors as well. So yeah, so okay, so we'll stop here, and we will then the quiz should now be open, so you guys can start the quiz. But I'm here for office hours. You can ask me more questions about this, or some if stuff comes up in quiz, I'll be online. Oh, so there's